we need to show that if x be any real number, then this limit is equal to 0. And also we need to show that this limit is equal to infinity. Now there are some theorems that help us to solve these kinds of examples. Let's read them. These are very important ones. Let Sn be a sequence such that Sn not equal to 0 for all n, and limit n tends to infinity Sn plus 1 divided by Sn equal to L. Now there are two conditions. If mod L is strictly less than 1, then limit n tends to infinity on Sn. That will be equal to 0. And if L is strictly greater than 1, then this limit comes out to be as infinity. So on the basis of this theorem, we are going to solve those examples. So first part, we need to show that limit n tends to infinity on x to the power n divided by n factorial is equal to 0. For that, let's consider Sn to be x to the power n divided by n factorial. Now here it is given that this x be any real number. That means x can be equal to 0 or x cannot be equal to 0. Both the case can happen, right? So we need to discuss both of these. So case 1, if x is equal to 0, then what would happen? This Sn is equal to 0 for all n belonging to the natural numbers. And so if you take the limit on this Sn, that will be obviously equal to 0, right? The second case, if x is not 0, then Sn is non-zero for all n belonging to the set of natural numbers, right? And we know that from this theorem, if Sn is non-zero for all natural numbers, then we use this limit. We find this limit, right? So let's find limit n tends to infinity on Sn plus 1 divided by Sn. So this is limit n tends to infinity. What will be Sn plus 1? From here, Sn plus 1 is just replace n with n plus 1 divided by n plus 1 factorial. So we are writing this Sn plus 1. And then it is divided by Sn, that is x power n divided by n factorial. So from here we cancel this x to the power n and we get x in the numerator, and n plus 1 factorial is n plus 1 into n factorial, and also we are having n factorial in the numerator, so these two cancelled out and we have x divided by n plus 1. So when taking n tends to infinity on this, we get x divided by infinity, that is equal to 0. So this is equal to 0. So we are getting limit n tends to infinity on Sn plus 1 divided by Sn to be equal to 0. And if I take the mod of this limit, that will be also equal to 0, right? And if the condition is what? If the mod limit L is strictly less than 1, then the limit n tends to infinity on Sn is equal to 0. Yes, this 0 is strictly less than 1. So that means the limit n tends to infinity on Sn. What is Sn? It is xn divided by n factorial. This will be equal to 0, right? From the theorem. So now let's move on to the second part. Here we need to show that this limit is infinity. So let's take our Sn to be to the power n divided by n, and clearly this Sn is not equal to 0 for all n belonging to the natural numbers. There is no x, right? Only n. And we know that from the theorem, if Sn is non-zero for all n belonging to the natural numbers, this is the theorem, and limit n tends to infinity on Sn plus 1 divided by Sn. If it is equal to some limit, say L, and if this L is strictly greater than 1, then we get limit n tends to infinity on Sn to be equal to infinity. So this is what we are going to do here. So this theorem we are going to use over here. Let's find out this limit L first. So limit n tends to infinity. What is Sn? It is 2 the power n divided by n. But here we need Sn plus 1 divided by Sn. So limit n tends to infinity, Sn plus 1 becomes 2 the power n plus 1 divided by n plus 1. And Sn is 2 the power n divided by n. So this becomes limit n tends to infinity. This is 2 the power n cancelled out with the numerator and denominator, and here we have n divided by n plus 1. And if I take n common from the numerator and denominator, I get 1 divided by 1 plus 1 divided by n. And now putting n tends to infinity over here, I get 2 into 1 divided by 1 plus 0, and that is equal to 2. And this 2 is strictly greater than 1. And whenever L, the limit strictly greater than 1, then the limit n tends to infinity on Sn comes out to be infinity, right? So from the theorem on limits, you may write that complete theorem over here. Limit n tends to infinity on Sn is equal to infinity. Reason, because L is strictly greater than 1. Right? Because the limit we have found is strictly greater than 1. So that is why this limit is equal to infinity on Sn. That is, limit n tends to infinity on what is Sn? It is 2 the power n divided by n. That is, this limit is equal to infinity. Okay, thank you.